Hey, John here. Let's look and see how we can use some of the extra memory banks on our Z80 Retro board as a cache for the SD card. Let's start by get a little terminology and a quick review of where we are. So, number one, what is a cache? In the simplest of terms, it's a plurality of buffers that we refer to as slots or lines, depending on different manufacturers, architectures, and systems. You tend to refer to cache lines when you're talking about a cache inside of a CPU that caches blocks of memory. Those blocks are usually referred to as lines. Quite often you'll hear cache systems, the blocks of data that are in there, the buffers that are in the cache, referred to as slots in other scenarios. I'm going to use the word slot to refer to the buffers that we're going to put in our cache, because that's what I'm accustomed to doing. Okay, so a couple of observations. A typical cache usually has a power of 2 number of slots, for reasons that we'll see as we go along. Almost everything in computing, because it's binary, the numbering system is based on powers of 2. Whenever you have a quantity of items, or what we call a natural alignment of something in a machine that uses binary numbers, making things powers of 2 is always a simplification when it comes to things like how many bits you use to represent a number, how many gates there are, how many wires on a data bus, all that sort of stuff. It's in binary, so you see, once again, the powers of 2 proliferating into everything. Just like humans do when we count in decimal. Powers of 10, our natural number base that we use, infiltrates a lot of what we do, right? Okay. Cache slot normally, is sized to match the natural size of whatever your data exchange is that you're trying to store, in your cache. So in this case, we're going to use them to hold our SD blocks. Our SD blocks are hex 200 bytes in size, which is 512 in decimal. So what we're going to do is we're going to create a cache that has some plurality of slots. I'm going to put 256 slots in there because that's a nice power of 2. In fact, it's a nice round power of 2 because it's also a power of 16, and we can express it in hex and make it easier to write down and talk about and visualize in our heads. Okay, so we're going to have 256 slots, each of which are 512 bytes in size. Now remember, in our first draft retro BIOS, we have what you could call a 1-slot cache. Okay, we have one place, there's a buffer at the end of the BIOS where we can store 512 bytes, and we have to do that because we have to exchange 512 bytes with the SD card if we want to exchange anything at all, because it's the natural size, it's the required size of a block transfer into or out of the SD card. So we have arguably a 1-slot cache right now, and we use that slot to hold 4 CPM sectors or 1 CPM track. Okay, now let's make an observation. When you only have 1 slot, we always know which slot we need to use. It's the one that we have. Okay, now what's the point of a cache? Now, a cache, the entire difference between what we have now, our 1-slot cache, and a general one, is that we would like to have more than 1 slot. The idea being, and as we saw earlier in CPM, when we read from the disk, quite often, you log in a disk, they say when you like warm boot, it will scan the directory, right? It's going to read many sectors in order, and then later on it might have to go back and access those sectors again when we open a file or we want to execute a program by reading the executable data out of the file into the memory and then invoke it to run it as a program. So the idea is, if we have more than one, after we've done something like scan a directory, all those directory blocks might still be in our cache. So later on, if you type dir, it doesn't have to reread the whole thing every time. Or if you run a program, it doesn't have to scan the directory looking for the program. Or shall I say, it has to scan the directory, but it doesn't have to reread all the blocks from this SD card when you go to execute that program, because it will know where all the sectors are, because it has the directory still, presumably, sitting in its multiple slot cache. So that's the whole rationale behind getting rid of our one slot design and putting in a cache that has multiple slots. So, given, right, CP/M file systems have hex 80 byte sectors. They're numbered from 0000 to FFFF in hex. That means there's 64K, we say, in decimal total sectors, maximum, I should say, sectors in a CP/M file system, because that's how CP/M was designed, period. Therefore, we have what? That's the total number of sectors, because they go from 0 to FFFF. Therefore, the total number of them is 1 followed by 4 zeros, times their size, hex 80, which is 128 bytes in decimal, that's 64K. You multiply those together in hex, and you get 800000, which, by the way, is 8 megabytes, which is why the maximum size of a file system in CP/M 2.0, or 2.x anyway, is 8 megabytes. It's because the sectors must be this big, and there can only be that many of them. All right, period. That's our size limitation. Okay, so what do we got here? When I designed the Retro BIOS and we put our disk parameter table together, I went through all the details on that and why we did what we did. I decided that it would be 4 sectors per track, and therefore one track was the exact same size as one SD card block. To make it really simple for us in our BIOS, we don't have to translate between the two, and there's really no reason to do it any other way. This is just really a convenient coincidence that things came out this way. So therefore, what do we have? The total number of SD blocks is going to equal the total number of tracks in our CP/M file system, which is the total number of sectors divided by 4, because there's 4 on each track, aka 4 on each block, which is hex 4000, which is decimal 16K. So therefore, in hex, they go from 0000 to 3FFF. Okay? Now, I've arbitrarily chosen that the cache we're going to design today will simply have 256 slots, hex 100. All right, they're going to be numbered 00 to FF in hex. Why did I do that? Because that's a very convenient size when we're dealing with binary numbers. This value can fit in an 8-bit byte. You know, if I made it, maybe I wanted 200 in hex slots, 512 instead of 256. Well, then you'd need a 9-bit number, which is a little more awkward to talk about. You can do that. There's nothing stopping you, but it's more convenient if everything comes out in nice even multiples of hex digits when we're drawing up our notes here. So I've just arbitrarily chosen that's how many slots we're going to have. Now, there is some guidance here. You can't choose more slots than you have data to hold all the bytes that you can put in all those slots, right? We only have so many banks of memory. We could have 512 slots if we wanted to. It would use up half of the memory in our system. We can't use up all the memory in our system, because then we need to, we need a place to put our programs and stuff. So you can use as many slots or banks of memory and convert those into slots and figure this number out as you go. All right. I've just chosen this because it's big enough to be interesting and small enough to actually fit in the memory that we have. All right, so my first design that I'm going to use is what we call a direct mapped cache. And what that means is where the data goes that we're going to store in our cache has no options whatsoever. It is what we call directly mapped. In other words, the slot within which we're going to put our data, and we're going to read in blocks of data off the SD card. Where do we put them? In our 256 slot cache. Which of the 256 slots should it go? Well, it's going to go in the one and only slot given by these bits here in the low order byte of the CP/M track number, which is also, you could call that the SD card logical block number, because it is not the actual physical SD card block number, because remember, the partitions on the SD card can move around on the SD card. So the CP/M track number is more convenient, certainly for this discussion, But keep in mind that the CPM track number plus whatever the offset is to where the partition is on your SD card is how you convert your CPM track number to your SD card block number, right? And I talked about all that before. The current version of the BIOS, as I record this, I believe the CPM track number 0 starts at SD card block number hexadecimal 800 or something like that, okay? So don't confuse all this. We're talking about the CPM track numbers right now. So any CPM track number that ends in a hex 00 must be stored in our cache slot number 0. So that means if I say, oh, I want to read in and use the data from CPM track number 0, that's 0000. That means because these are zeros, it must go in slot 0. Okay. And it also means that if I want to read in later on track 0100, that new track must also go in slot 0, therefore discarding what was in there before. Just like when we use our 1-slot cache, every time we need a new track read in, we have to throw away what's there now and remember which the new one is, and of course read the new one into our 1 slot. In this case, we just simply have 256. We cannot use them willy-nilly because it is direct mapped. We can only use the one and only 1 slot that is given by the least significant 2 hex digits of our CPM track number. So you could think about this for a minute. There's some strategy to pick which bits you're going to use out of your CPM track number to define as your slot number over here. If you choose poorly, this doesn't work very well. For example, a poor choice would be to use the most significant 8 bits, because we already know that it's common in a CPM file system to read the sectors and therefore the tracks in order as we go from 0 up to some size, especially when we're scanning through the directory. If every single track use the bits up here as their slot number, and we go through the directory, it turns out we're going to then use, it would be a 00. I think the first directory track number is like 20 in hex, and then 21, 22, 23, and so on, right? Well, if we use these bits over here for the slot number, then what happens is every time we read a directory block off the SD card, we have to delete the old directory block because they'll all fit in the same slot, because all the directory tracks have the same value in these bits over here. Okay, what we want to do is make the slot numbers vary as often as possible is our goal, instead of as least as possible, so that we spread our data around in the cache. Okay, now there's not always the right answer. No matter what you do, you're going to end up in a situation where there's going to be what we call a collision. And for example, if I read in a directory sector from track 0020, and I decide, hey, I'm going to put that block in slot number 20, okay? And then later on, I'm going to read in the one that's on CPM track number 21. It'll go into slot 21, and then I'm going to go to 22, 23, 24, 25, and then so on. Once I get all the way up to hexadecimal 100, and then I go to 101, 102, 103, 120, 121, and so on, it will override all of what used to be in there. So it really depends on how much data you read and the order in which you read it and write it, or more accurately, exchange it with the SD card, that will determine whether or not this is really going to be useful for you or not. Okay, so be careful. There's different kinds of caches, and they have all different pros and cons. So this is all part of the decision-making process. This one is really simple to implement, so it's where I'm going to start. Okay, so what's all this other stuff? All right, so what do we know if we do this, right? Well, we're going to use the least significant 8 bits to represent which one of the slots, I'll explain the tag thing in a minute, out of our 256 slots, okay? What do we do with the rest of these things? Well, it turns out that the total number of tracks that we can have on our disk, as I said before, is actually 3FFF. because there's 4 sectors per track and a maximum of FFFF sectors, these top 2 bits in the track number are always going to be zeros, okay? So it turns out that these 6 bits in here represent the total number of possible tracks that will all have the same slot number down here. Like I said, 0020 has the slot number 20, okay? 0120 also has a slot number 20, and so on. So it turns out this means there's 64 total CPM tracks that could be in any given slot in our cache, in our 256 buffers, our slots in our cache, right? So we need to keep track of which one is in there at any given time. We also have to keep track of the fact that there might actually be none in there. Again, I talked about this before when we talked about the reading and the writing routines on our SD BIOS routines, because when it boots up the first time, there isn't any data in there. It's garbage, right? So we could actually have one of 65 possibilities. It could be 0020 in slot number 20. It could be 0120, 0220, and so on, up to 64 total possible actual tracks. Plus, it might actually never have been used and have garbage in it, okay? So we have to keep track of that. That's what this tag table is for, okay? So a cache tag is a value that remembers which one of however many possible data blocks is in our actual cache slot at any given time. So what we need to do is we're going to build we're going to allocate a region of memory in our extra banks on the retro board, and it'll hold 256 slots, each of which will be 512 bytes in decimal in size, okay? Then we're going to build this table that's going to have 256 bytes in it. And in this table, we're going to store this value over here. So what happens is when we look at slot number 20, we're going to look in the tag table. We're going to go to element number 20 and hex. And then we're going to say, is the value in here equal to this value over there? If these two match, then that will represent a situation where the cached value over here in the slot number 20 is the one that matches the one that's been requested. If later on it comes along and says, I want to read a sector that's on CPM track number 0120, it'll look in here and tag for slot number 20, and it will see the previous value, which in this example was 0020, and it'll see that the value in here would be 00 in that case, and I want 0120, and it won't match. So what does it do? Again, it does what we did before when we only had one slot in our cache, and it says I have to reuse this because it cannot go anywhere else because the slot number must be 20, and therefore what it'll do is it'll abandon the data that was there, read in the one requested, the 0120 block off of the SD card, update the tag to remember that the one now is 0120, so that any other accesses to slot number 20 can then use this information to make sure it's the one of 64 possible tracks that it might want to access in there, right? So this is how we're going to keep track of this. Okay, so the tags table keeps track of which CPM track is currently in a given slot, and we use this, of course, we use the tag table for that. Now, it should also be apparent, I hope, that if we store an 8-bit value in our tag, we only have tracks that can go up to 3FF. If we set all the bits to 1 in here, that might be a good value of a tag that represents the situation where we can say, I never put anything in this slot and it has garbage in there. Because that's what we call like a sentinel value. It's illegal. It can never happen in a normal circumstance because a track number can never have bits of it. They can never be FF in here because the track numbers don't go that high. Therefore, we have a nice convenient value we can put in this table, which would be an FF for all the slots in here that says there's nothing in the cache slot for this slot number. Okay. So that's what we're going to do. to keep track of what is where. Before we decide where our slots are going to go in the memory of our retro board, let's review where our memory is in our retro board, okay? So quick recap here. This is a diagram I've showed before. We have 16 total banks of 32K each out of our half megabyte RAM, okay? Banks 0 through 14 can be used and mapped into the low half of the 32K address space of the Z80. Bank number 15 is hardwired so that it always appears in the top 32K of the memory space on our retro board. Talked about this at great length earlier. You can go back and watch the other videos and we reason all this out and how the thing boots and how we decided which bank is going to be used for what. Short of it, spoiler alert for those of you watching videos in reverse, I arbitrarily chose that bank 0 would be the bank that we used to hold the bottom 32K, since it really didn't matter as long as I did not choose bank 15. Because obviously, if I chose bank 15, it would be the top half and the bottom half at the same time. And while you could use that, it doesn't make a lot of sense in most situations and can be confusing. Because if you modify bank 15 when it's mapped down here, you're also modifying it at the same time as what's up there. It's not too useful for CPM to do that. But it turns out to work that way because of the simplicity of the design of the decoder. It reduces the number of chips and stuff in the design. Okay? Now, I could have chose any other bank in here. It just seemed natural to choose bank 0. And that is the sole reason that I chose bank 0 for the lower half, because it seemed right at the time. As we'll see today, it might be optimal if I chose something else. And the reason is because if you think about it, we want to have 256 slots in our cache, and they're labeled 0 to 255 in decimal, or 0 through FF in hex. Each one of those is a half a K. Therefore, we have 128K of memory slots that have to be mapped into these banks somehow. And we can extend our concept of direct mapping, and that's the key here, for the slot numbers to where they go in our RAM. Which bank does slot number 20 go into? I don't know. We have to decide that mapping as well. Now, it turns out that with 256 or hexadecimal 100 total number of slots, what did I say, 128K, each one of these is 32K, therefore we need 4 banks total to hold all of those slots. Well, which banks should I put them in? I could use banks 1, 2, 3, and 4. I could pick banks number 14, 13, 12, and 11. I could pick banks number 10, 11, 12, 13, or whatever, okay? Which ones I choose will make it easier or harder for us to write the code to figure out which bank has any given slots in. As I said before, just like with the cache and the direct mapping, things that have a power of 2 in terms of its quantity and or size, and things that have an address that begin on a multiple of their size are the easiest ways to deal with all this stuff. We'll see why in a minute. So, all of our slots have a power of 2 size. Our entire cache, the number of slots, is a power of 2. The amount of memory is a power of 2. Starting with bank 1, not a good idea. It's not a power of 2. We have 4 banks of memory that we need to allocate to this. So it could start at bank number 4 and then use 4, 5, 6, and 7. But we'll see, it would be really great if we could start at bank 0 and go 0, 1, 2, 3. Okay? Because if we start at bank 0, as we'll see, we have to do no math at all. We just extract bits out of our number, and that equals the bank number. If you say started at any other one, then we're going to be adding some, like, here's your first one of n, and it's not too bad. I think it'll boil down to a single add instruction in our driver that decides where the slots go, but it works much better if everything starts on a power of 2 boundary and that sort of thing. So my gut tells me, and honestly I haven't implemented this yet, I'm just reasoning it out as I go here, that this bank 0 is probably not a good choice. I probably should have chosen to store by default all the memory of the low half of the RAM over here in bank 14. There's only one of these banks that's used for that. There's only one bank that's used for the top half. And I showed you already why we chose bank 15. With them all set to 1s, we can use OR gates. We have a chip that we can actually buy that will work correctly. And we don't have any fancy stuff going on as long as I chose bank 15 for the top half. So this was done to save money because I can actually buy a chip that'll do that. The other bank for the low order, like I said, doesn't matter which one we choose. I probably should have chose bank 14 instead of 0. That's all I'm saying. So as we go through this, let's figure out how to best, choose. We might want to move it over here. It's really no big deal which one we choose. As you might recall, here is the firmware. The first instruction of the firmware is the thing that assigns which memory is going to be used in the low bank, after which point we never change it. It's just what value goes in the accumulator, and I stick it into the latch that drives the address for those most significant 4 bits. That's what happens here. And we talked great length about this before. Then later on, when we warp into the BIOS, after the flash boots, as you recall, it'll jump to the load base address, which in turn jumps down here to the BIOS boot routine, which starts at this label right here, and it does the exact same thing the flash did, arbitrarily choosing low bank number 0, because we had to pick 1, as long as it's not 15, right? And it does the same thing again over here, at which point it never changes it again in this current release, okay? It could be just as easily configured to select bank number 14 instead of 0 at this point. It doesn't know or care at this point in time which one it uses, okay? So keep this in mind as we think about and strategize about which banks should be used to hold our cache slots, okay? Remember that we get the slot number from the CPM track number by simply ignoring the most significant 8 bits, just using the bottom 8 bits to directly map into our slot number. Now, given that slot number, we can look at it like this. If we use the most significant 2 bits of our slot number and just simply say, ignore the rest, these 2 bits, what do we get? We get a number between 0, 1, 2, and 3, right? That's our, just done. We're going to call that our bank number. Just use those 2 bits to represent which one of the 4 banks our slot must be within, right? Then we use the rest of those 4 bits to determine where inside that bank the slot is located, all right? So if we take these 6 bits and we move them into this position of a 16-bit number, and we set these outside 2 bits to 0 and the bottom byte to 0, then this result is exactly equal to, you could say, the offset within a memory bank where that slot will go. But since our memory banks start at 0, the offset is the actual address of the beginning, the first byte in any given slot, in any given bank, can be determined by just taking these bits, shifting. Look what we got here. We shift this thing left once, throw away the B's. Once you're done with that, you just shift this left, you end up with this, followed by this 0. You then end that with a 7E, and you end up with this 0, whatever the 6 bits are here, followed by a 0, and then you just simply set the register that holds the least significant 8 bits to 0. And you would then have converted this directly, again, into the actual address that you can use if you take these 2 B bits and stick it in the memory bank latch, all right? So when you're done with all that, But we'll see again if you use these bits. You can use it however you want. The goal would be to choose the bits in such a way that the amount of shifting and ending and oring and adding and whatever the math is that you need to do to convert this into the bank number and convert that into this address number is minimized, because no matter how you slice it, it turns out it doesn't matter which bits are used for what in this particular scenario. It did matter when we tried to figure out how to calculate a slot number from a track due to the nature of what it meant in a file system and how the operating system accesses the blocks and in what order. But it turns out when the whole thing's in memory here, and it's just a matter of which one is where, it really doesn't matter how much spaghetti gets involved in this particular aspect of the process. So we'll choose math once we start writing the code to minimize the amount of instructions that it takes to do our work. Turns out this is probably not too bad, because as I just described, you can do a single shift and a single and you can end up with this value here. These two bits that select the bank number ultimately need to be written out into the bank select latch. And it turns out that if we use the first four banks, 0 through 3, we'll have to, as we will see, shift this right 2 places and have 2 zeros followed by the 2 B bits in order to get this value into that latch. It turns out that's probably not too bad. But again, we'll revisit all that when we actually write the real instructions. Okay, so how then do we make this next leap? What do we do with this? Well, we know that we need 4 banks, and 2 bits gives us a number 0 to 4, so we'll use that, and we'll poke that in our bank select latch. That'll select which of these banks will appear in the bottom 32K. Okay, provided that we're not using bank 0 to hold the TPA, and we instead put the TPA in some other bank. This will work as is. Then when we're done with that, if you look at these bits and think about it, slot number 00 in hex, where would that go? Well, these 2 B bits would be 0, therefore we know it must be in bank 0. And if it's 00 in hex, then all the A's are 0, so that turns out to be slot 0, which if you do this, all these will be zeros, all these will be zeros, and therefore the offset or the actual address within this bank will be 0 of bank 0, and the math all works. Well, what if I need to go to bank, slot number 1? Well, that would be 0, 1. So that's these 2 bits are 0. It's in bank 0, and this will be 0, 0, 0, 0, 0, 1. Shift it to the left, hand it out, do this. You end up with a 0 hex here, and that's a 2. So that'll be a 1, 0, and then all 0. So that's 0, 2, 0, 0. And as you can see, I've written these values out down here, and that is the memory address of the second slot. No matter what it is, whatever the bank you're in, that's the second slot. Beginning of the second slot, third slot, and so on. The last slot in any given bank will be at 7E00. Again, so this is the way we can make all that stuff work, right? So let's double check. Let's say we want, slot number, whatever. This is going to be 128 in decimal, a hex 80. Okay. Check my math here. Well, 80 in hex is a 1 followed by all zeros. So that would be 1, 0. Throw that away. That's the number 2, so that means I need bank 2. So far, so good. And I said it's bank number 80, so all these bits will be zeros. Therefore, all this is 0, and the offset should be 0 within that bank, and that works. What about 81? Okay, same thing. We got an 8 here, so that's 1,000,000. So that's bank number 2, right? 1000. That's a binary 2. And then 81, I said. So this is a 1. So a 1, when you extract these out, you end up with all zeros followed by a 1 right there. And that's an hex 0200. And that's exactly what you want for bank 81. If you do a BF, what do we get there? B is a 1011 in binary. Okay. So again, we have the 10. That means it's bank number 2. Done. And then a BF. So that's 8, whatever, 9, A, and B. So that'll be all 1s over here. That makes a lot of sense. It's the last one. We would expect that to be the case. So if we put all these to 1s, we end up with, what's this? A 0,111 is a 7, and a 1110 is an E. And that's always going to be 00 over there. So that's what I said would be the address of the last slot in any given bank would start at 7E00. 0, 0. So we can now see how we can take a CPM track number and directly map it into a slot number. And we understand that because we have more tracks than slots, if we have two tracks that want to be in the same slot, we have to throw the old track away, the data away that's in this slot for any given track, if we need to reuse it for a new one. All right. And that happens because the bottom two hex digits, given this particular scheme of doing the mapping and the number of slots and everything, that any track number that ends with the same two hex digits has to occupy the same slot. Okay. And we also know that given a slot number, we can convert it directly into a bank number and a memory address within that bank wherein that given slot will begin. We can store a total of 256 slots in here, and we cross our fingers that using this scheme will result in a fairly good percentage of utilization of our cache. In some cases, it will work. In some cases, it won't. It turns out this will work very well if you sequentially scan through the disk over and over and over again in the same tracks, which is always the case when you're accessing the directory on a CPM file system, just due to the nature of how the thing is designed. It may not work for other apps, right? When you load a COM file and run it, you might load a different COM file later, and by the luck of the draw, those various data blocks that hold all the code for the COM files or the data files that those COM files open up might actually have track numbers that end in the same digits as, say, for example, the blocks in the directory. And then when you run those, it'll turn out that it overwrites all the directory blocks. So the next time when it's done and you got to reread the directory, you'd have to reread the directory in, and then it would rewrite over the blocks used by that COM program. And maybe you'd run the COM program again, and then it would have to rewrite over the directory data tracks again. And you could go back and forth, and it wouldn't give you any real benefit. Okay. If that happens, you have to up the ante and use a more sophisticated design for your cache so that you can have more than one way, is the word that everyone uses, to store in a given slot, rather than pigeonholing it into one single slot and saying you don't have any other options. You can, in its simplest of terms, maybe we have more than one of these sets of blocks, and you could see, could I put it here? Maybe yes or no. Maybe I'll allocate 4 more blocks over here and do the same thing and say, well, maybe I'll put it over there if this one's busy. But if they're both busy, well, then I'm in trouble again. Eventually you run out of resources. But those other kind of designs have different names. They have things like a set associative cache, or n-way associative cache, or a fully associative cache, and so on. And those get more sophisticated, and we can talk about them later on. I suspect this will work fairly well. In the meantime, it's better than a one-slot cache. So next time, we'll walk through some code that we can use to implement all this and see how it does. Thanks for watching. I'll see you next time.